Welcome to this explainer. Okay, today we're tackling a massive, sometimes totally overwhelming topic, but we're going to break it down into something you can actually visualize. So instead of thinking about the modern data landscape as some invisible cloud or endless spreadsheet, I want you to picture it as a giant, bustling factory, right? Raw materials go in, heavy machinery processes the whole shebang, and boom, valuable finished products come out on the other side. Today, we're taking a full end-to-end tour of that factory to really nail down the absolute basics of business analytics.
It's kind of crazy when you think about it. We are generating quintillions of bytes of data every single day. That's a scale that's almost hard to wrap your head around. Every click, every swipe, every sensor reading, it's all data. But here's the catch. Having a massive warehouse literally overflowing with raw materials, it doesn't actually help you if you don't have a reliable system to extract its value. I mean, all the data in the world is completely useless unless a business can step up, process it, and transform it into real insights to make better decisions.
Okay, let's dive into our roadmap for today's explainer. First, we'll look at understanding business analytics. Second, we'll meet the data dream team. Third, we're dealing with data sources. Fourth, we'll get into data mining and machine learning. And finally, we'll wrap up with real-world applications and business challenges. Let's get to it.
Section 1. Understanding business analytics, the what and why.
Now, before we go a single step further, we absolutely have to clear up this incredibly common mix-up. Business analytics is not the same thing as business analysis. I know, they sound almost identical, but they do completely different things. Business analytics, that's all about the data. It's using statistical analysis to dig into past performance and forecast the future. Business analysis, on the other hand, focuses on functions and processes, figuring out business requirements and solving specific operational problems. So one is driven by data and the other is driven by process. Huge difference.
And in the real world, this analytical process, it's not just a one-and-done straight line. It's totally continuous and cyclical. You don't just start crunching numbers for the fun of it. First, you discover a specific business need. Then you collect the data. You analyze it, you predict outcomes, you find the absolute best solution, and finally, you make your decision. And after that, the cycle starts all over again the second a new business need pops up. It's this fantastic iterative exploration.
Within that continuous cycle, we generally use four main types of analytical models, and it helps to think of these like a staircase going up in complexity. At the bottom, you have descriptive analytics, which just asks what happened. Like, hey, sales dropped yesterday. Step up to diagnostic analytics. Why did it happen? Oh, right, a massive snowstorm kept everybody home. Next is predictive analytics. What is likely to happen? Looks like it's going to snow again next week. And finally, right at the top, prescriptive analytics tells you what to do. Put the snow shovels on sale right now. You're literally moving from simple hindsight up to foresight and straight into automated optimization.
Section 2. The data dream team. Who operates the factory machinery?
All right, let's look at the people running this place. There's a stark contrast between two very popular roles you hear about all the time, the data scientist and the data analyst. Now, a data analyst is basically living in the present and the past. They provide these static insights using descriptive statistics, and they usually aren't the ones making the final executive decisions. A data scientist, on the other hand, is all about the future. They're using dynamic machine learning algorithms to unearth upcoming trends, and they actively participate in making the big decisions that steer the entire company.
But, and this is a big but, neither of those roles can do their jobs without our third key player, the data engineer. These are the folks who build the foundational platforms, the architecture, and the pipelines that the scientists and analysts actually rely on. And there's a big difference in the raw materials they handle, too. While analysts usually stick to neat, structured data, both scientists and engineers have to get their hands dirty wrangling messy, unstructured data as well.
So the really crucial takeaway here is that because these roles are so distinct, they use entirely different sets of tools. Analysts are mostly living in visualization software. Think Tableau, Excel, and running SQL queries. Engineers are deep into big data tech and heavy systems, using stuff like Hadoop, Apache Spark, Kubernetes, and Java. And data scientists, they're leveraging Python, R, and SAS for all that heavy-duty statistical modeling and machine learning.
Section 3. Dealing with data sources, the raw materials.
Obviously, the very first step in any analysis is getting your hands on the raw material. This broadly splits right down the middle into primary data and secondary data. And then if you look at secondary data, that splits again into internal organizational data and external agency data.
The real difference between these branches comes down to three things: time, cost, and originality. Primary data is the fresh stuff. It's raw, original data extracted directly from the source specifically for whatever you need right now, like running a brand new customer survey. Secondary data is just previously recorded information that you're reusing. Now, internal secondary data, like your own company's past sales records, is super fast and cheap to get. External secondary data, like massive government census records, might take a bit more time to wrangle, but it gives you an unbelievable amount of information.
So how are we actually gathering all this today? Well, the methods are wild. They range from traditional to totally sci-fi. You've got the Delphi technique, which is actually named after the Oracle of Delphi from ancient Greece, where you gather a specialized panel of experts. You've got your standard focus groups and really rigorous experimental methods. But today, oh man, we also have IoT sensors built straight into your home appliances, tracking performance in real time, and literal satellites collecting terabytes of surveillance data every single day. It's amazing.
Section 4. Data mining and machine learning, the machinery in processing.
Now, a lot of people think data mining is this brand new tech fad, but it's really a centuries-old evolution. It actually started way back in the 1700s with early statistics and Bayes' theorem. Then in the 1960s, we hit the computer age, with static data stored on literal physical tapes. By the 80s and 90s, relational databases and data warehousing became the big thing. And today, the massive surge in computing power has evolved all of that into proactive, dynamic systems crunching big data with huge algorithms. You might be wondering, wait, isn't data mining just doing statistics? Actually, scratch that. No. There's a very sharp line between the two. Traditional statistics generally sticks to numeric data, handles smaller data sets, and focuses on analyzing and presenting what's already there. Data mining, though, that handles massive, complex data sets with both numeric and non-numeric data. And most importantly, it's an inductive process. It's designed to literally generate entirely new theories and patterns from the data, not just describe it.
There's this fantastic quote from Usama Fayyad back in 1996 that hits the nail on the head. He described it as the non-trivial process of identifying valid, novel, potentially useful, and ultimately understandable patterns in data. Data mining is really just one crucial step in a much bigger journey called knowledge discovery in databases, or KDD. Because you can't just find random patterns, right? The insights have to be valid, they have to be new, and they absolutely have to be understandable so a business can actually take action.
Section 5. Applications and business challenges, finished goods and safety regulations.
So what does this all mean for us? Why does it matter? Well, because this data factory literally shapes the modern world. In retail, analytics dictate exactly how a store dynamically prices products based on buying habits. In healthcare, it's organizing massive clinical systems and tracking patient health indicators. Credit rating agencies use it to predict your future spending patterns. It is completely revolutionizing supply chains, logistics, HR, and even how professional sports teams plan their game strategies.
But look, it's not all sunshine and rainbows. To run this factory safely, companies have to put some serious guardrails in place. They face massive hurdles around privacy and keeping customer data anonymous. They are constantly fighting off hacking and insider threats. Plus, internally, there's often a huge lack of technical skills or just plain resistance from employees to adopt these new tools. And at the end of the day, it all depends on data integrity. If you can't keep your massive data sets clean and accurate, your predictions are basically worthless.
Which brings us to one final, absolutely critical question. In a world that is spinning out quintillions of bytes of data every single day, just having a warehouse full of raw materials isn't going to cut it. You need the right team, the right tools, and the right processes. So is your organization just hoarding static numbers on a server somewhere? Or are you actually mining it, analyzing it, and discovering true knowledge to drive things forward? Definitely something to think about. Thanks so much for joining me on this explainer, and keep exploring.